So here's our simplest electrolytic cell. We have a simple salt. Now, with electrolysis, the charges need to be able to move around. You can't just put 2 electrodes into a solid. You can't put it in a solid salt, even a little grains of solid salt, because even in a solid, all the particles are stuck in their position. They can't move around. And if we're going to have current flowing, there needs to be charges that can move. You have to have mobile charges that can move around. So if you electrolyze a salt, the salt must be in the liquid phase. So we need to heat the salt up so that it melts down to a liquid, and then we can put our electrodes in and run the power supply. So really this is not practical for us to do. Out in industry, I don't know, maybe they melt salt down and do that. Salt has a very high melting point. It's like 700 degrees Celsius or something like that. So this is not practical at all for us with our equipment to be able to do. So it has to be melted down to a solid, melted down to a liquid. And I want you to also keep in mind that salt, sodium chloride, is a stable substance. We don't ever see sodium chloride just naturally breaking apart and making neutral sodium and neutral chloride. We don't ever see that. When we go to the jar of sodium chloride or grab a salt shaker to use sodium chloride, we don't ever shake that thing and have this yellow gas coming out of it for chlorine. That doesn't happen because sodium chloride as a compound is far more stable than sodium element and chlorine element. So when sodium and chlorine are around one another, they spontaneously join together and make sodium chloride. So that means that the forward direction is spontaneous. Electrolysis is able to cause the reverse reaction to happen. It causes the reaction to go in the non-spontaneous direction. So that's what I'm saying here. Spontaneous in the forward direction. If we want the reverse to go, we're going to electrolyze it. And so electrolysis would be set up like this. We would have salt that gets heated up and melted down to a liquid. And then 2 electrodes are put into it. The 2 electrodes are connected to this power supply, and we turn the power supply on. Now, the power supply has, as you see on this power supply, I know this is kind of busy with cords coming off of it and wires coming out. Which easily tangle, as you see. Okay. So this is much better for seeing the power supply. I want you to notice there is a black cord and a red cord. And in the power supply itself, without the cords in it, there is a black port and a red port. Hopefully everybody can see that from where you are. I'm going to go ahead and put the wires in now. Every power supply color codes its 2 terminals or 2 electrode ports. The positive is always red, the negative is always black. That is a universal electronics kind of color coding. So we can see with arrows the direction the electrons are going into and out of this power source. Where the electrons are going in, that's always the positive terminal. Oh, I did that in the wrong color. What am I doing? Red is positive. Black is negative. So yeah, I always think of it like this. When you have a power supply, the negative terminal is always the source of the electrons coming out of it. So the electrons always come out of the power supply from the negative port and then into that electrode. So the electrons are coming into the power supply at the positive and going out from the negative. Now, if we have this power supply purposefully pulling electrons in to itself through the positive port and pushing electrons out of itself through the negative port, then whatever is attached to the positive and the negative, something has to be happening there. If the power supply is pulling electrons in from the positive, that means that whatever is attached to this electrode has to be giving it electrons. the electrons coming in have to come from somewhere. So in this liquid that the electrodes are in, there has to be electrons that are being forced into this electrode and pulled up into the power supply. So you only have one option. There are, in this liquid, there are sodium ions, Na positive, and chloride ions, Cl negative. Sodium has already lost an electron. Chloride has already gained an electron. Sodium loses an electron to become positive 1. Chloride gains an electron to become negative 1. So at the anode, and the anode would be over here, the cathode is over here. At the anode, something has to be giving off its electrons. Now sodium is already a positive 1 over here. I'll use a different color. So in this mixture, and it's not even a mixture, it's a compound. In this compound, sodium is already positively charged, chloride is already negatively charged. Sodium has no more electrons it can give off. Sodium is a positive 1 ion here. It already has a noble gas electron configuration. Losing 1 electron makes sodium a positive 1. Sodium has no ability to lose any more electrons. You might say, what about sodium losing another electron? Sodium is already, it's lost an electron, so it has a noble gas configuration. It is not going to get rid of another electron. The chloride, however, is able to give off an electron. Chloride has a noble gas configuration, but if the chloride ion gives that electron that it had gained away, it would become neutral chlorine. So chloride ion releases its electron, becomes neutral chlorine. Remember, neutral chlorine is Cl2, it's not just Cl. So that's why there needs to be 2 of them, is because chlorine is diatomic. So chlorine has the extra electron. Yes, it has a noble gas configuration, but it can get rid of that extra electron and just become neutral again. So if somebody has to give off an electron, it's going to be the chloride ion, not the sodium ion. Sodium ion is not going to be effective at getting rid of another electron. It is stable as a positive ion. Now chlorine is more stable as a negative ion than it is neutral, but if somebody has to give off electrons, it's going to be the chloride. So the chloride migrates over here. It gives its electron away, and we would see, because chlorine would be made, at this electrode, there would be a yellow gas being generated. That would be the chlorine gas that I've talked about in here. So we literally would see the yellow gas chlorine being produced here and then being kicked out. You'll see when I show you this electrolysis setup that at the electrode, literally, there's bubbles that form. I'm not going to electrolyze sodium chloride because I can't. I can't get sodium chloride hot enough and keep it hot enough and then put the electrons in, or the electrodes in, to get the current to flow. So I'll show you the electrolysis of something else. Now, the electrons go in here from the chlorine, which has become the neutral chlorine, and then the electrons come out of the negative port and into here. So there's going to be somebody who's forced to reduce over here. Electrons are coming in, and the power source says, hey, electrons are coming, somebody's going to have to take them. You decide. And so chloride ion has already gained 1 electron. It's not going to gain any more. You never see Cl becoming Cl negative 2 or Cl negative 3. It only gains 1 and then it's done. But the sodium has lost an electron to become sodium positive 1. Sodium is able to take that electron back and go back to neutral, and that's what it does. It says, okay, well, I know chloride's not going to take another electron, so I guess I'm it. If that's what sodium says. So the electrons come in here. These sodium ions are going to accept the electrons that are coming in here, and we would see this electrode would get coated with sodium metal. This sodium would be produced at this. So chlorine gas would be kicked out of this electrode. Sodium metal would be piling up on this electrode. We have to order sodium metal sometimes in our department, and this is how it gets made. They electrolyze sodium chloride. Yes?
So when it's molten salt is there water too present, or are the electrodes just directly connected to the sodium?
Yep, this is just liquid sodium chloride. And it's weird because we don't ever think of sodium chloride as a liquid. But as a solid, sodium chloride cannot electrolyze because the charged things can't move, they're stuck in position. So it's got to be melted down to a liquid. There is no water present. This is not sodium chloride solution, it's just liquid.
And then that breaks up into Na plus and Cl minus?
No, well, yes, the sodium chloride liquid is a liquid consisting of Na positive and Cl negative ions. So they're able to move around. And so as soon as we kick this power supply on with the electrodes in it, the chloride ions migrate here so that they can oxidize, and the sodium ions migrate over here so that they can reduce. Yep. And there's no migration if it's in the solid form. Yes?
When they pile up, are they in liquid form still?
When sodium forms sodium metal, I don't know if it stays as a liquid, or I don't know what the melting temperature of sodium is. I'm not sure. I assume that it just becomes solid, but if this stuff is held at 700 degrees or whatever the melting point of sodium chloride is, that may actually be above the melting point of sodium too, so it would just be liquid sodium in there.
Would they just be like, would chlorine, what would chlorine be?
Chlorine's a gas, so it's just going to bubble out.
Okay.
Chlorine's going to escape out. Because Cl2 when it's formed is a gas.
So just like kind of end out this side. Like this sodium. Would just kinda
Yes, yeah, it would be just produced at this electrode right here where the touching thing, where the electrode comes into to this liquid, sodium piles up on there.
So wouldn't it be the same effect as having an aqueous NaCl if they both break up into ions?
We're going to talk about aqueous because if you have aqueous NaCl, the sodium can reduce, the chloride can oxidize, but there's also water in here that can also reduce or oxidize. So that's going to make a difference. The water is going to. Yes? Mo? That's what electrolysis is going to do.
How would it work if the reaction is like isotopic, like the equilibrium reaction, where like they both converting to each other? So like if that happens, or like a redox reaction,
If you have a reaction at equilibrium, I've never been asked this question. So what happens then to a reaction that's currently at equilibrium if we try to electrolyze it? When you turn the power supply on, whatever is in this mixture that would be best at oxidizing would migrate over here. Whatever in the mixture is best at reducing is going to migrate over there. And I think the same exact thing is going to happen. Now I know that there is not one direction that's more favorable than another when you have an equilibrium condition, but the power supply is still going to force somebody to oxidize and somebody to reduce. So whichever thing in the solution is best at oxidizing is going to migrate there and oxidize first. And whatever's best at reducing is going to come over here. And we're going to see that. Yeah, I'll show you. When we have a solution, like if we have aqueous sodium chloride, we'll talk about that later this hour too. Okay, so yeah, and aqueous sodium chloride is kind of like at equilibrium too. It's just sitting there not doing anything. So this is an electrochemical cell, but it's different. It's different from the galvanic cells that we've talked about before. All right, so now often when you're dealing with electrolysis, often the question that they'll ask you is, okay, this substance is being electrolyzed. So the setup would be like this, and what they're telling you is what substance is in this beaker being electrolyzed. So the question will be, what happens at the cathode and what happens at the anode? You'll be asked, like, what is oxidizing at the anode, what is reducing at the cathode? And you'll have to identify that. Now, my next slide here is going to tell us, it's very easy when you just have an ionic compound that you melt down. It's very easy to identify who's going to oxidize and who's going to reduce because the same thing happens for all molten salts. The nonmetal, which had gained electrons to become negative, is going to get rid of those extra electrons and become neutral. So the nonmetal always oxidizes gets rid of its extra electrons. And the metal, which had lost electrons to become an ion, is going to gain its electrons that it lost back and become reduced. So when you have and we will do examples of this. Unfortunately, it's going to be tomorrow. But after you see some ionic things dissolved in water, which is coming next, you'll see that the molten salt, just the simple salts where there's no water present, are the easiest ones to predict what happens at the anode and what happens at the cathode. So let's go on and start talking about, well, what about when you have a solution, which is a lot more practical. A molten salt is not practical at all because they have such high melting points. You have to heat it up obnoxiously hot and then try to get 2 electrodes in there without burning yourself or scorching your skin or whatever, making sure that you don't splatter things out. This is not convenient to have molten salts at all. Hi.
I was taking the Spanish national exam.
Oh my gosh, you have a chemistry national exam coming up here this afternoon, yes? Are you doing the chemo? Oh, I thought you were.
No.
Okay. Some of you are, aren't you? Yeah. Are you, Tanya? And Ronan, are you? And anybody else? I know you are. Oh, I was thinking more of you had signed up to do. Brian, you're not doing it?
I don't know if I have time.
Okay. All right. So anyway, no big deal. I hope you did well on that. So yeah, when we have an ionic compound that's dissolved, before we get to solutions, let's talk just about water. Water is more stable than hydrogen and oxygen are as a unit. If you have a mixture of hydrogen and oxygen, they will spontaneously make water. So this reaction is spontaneous, and we can demonstrate this reaction because the production of water is a redox reaction. As you see, the hydrogen oxidizes, goes from 0 oxidation state to +1. So when water is made, hydrogen oxidizes, and oxygen reduces from 0 to -2. So we can actually determine what the cell potential is for this reaction because our half reactions, which we go back to this table, there it is. We'll do the reduction of water first. The reduction of water is right here. Water, with hydrogen being +1, reduces from hydrogen +1 to hydrogen 0. This is the reduction of water. It has a reduction potential of -0.83. It's not excited about reducing. It's because it's more stable as water. It doesn't want to change. In the same way, the oxidation of the oxygen in water, remember oxidation, you have to find water in the products of these. It's over here, right here. Remember, this is an oxidation, so the half reaction needs to be turned around. Water reduces to oxygen, so the oxygen is -2 in the water molecule, and it increases or oxidizes to 0 when it makes O2. So the oxidation of water is right here. It's got a cell potential of -1.23 when it's an oxidation. So all right, take a look at this again now. In the spontaneous direction, where hydrogen is willingly oxidizing and oxygen is willingly reducing, the raw cell, or the half reactions would have the hydrogen, this H2, has an oxidation potential when it makes water of 0.83. Oxygen has a reduction potential of 1.23. Add these two together. If you add these two half reactions together, let's see, they are not ready to add together. We would have to get the electrons equal to each other. This oxidation gives off 2 electrons, the reduction takes in 4. So we would have to multiply this top one by 2 and then add them together. Remember, when you multiply the half reaction by 2, you do not affect or change the reduction or oxidation potential. So what do we have here? We have 4 hydroxides plus 2 hydrogens, and not H plus, H2s, making 4 waters. add that red reaction, half reaction, to this one. Oh, and this was plus 4 electrons. That's why I had to multiply by 2. The 4 electrons cancel out. The 4 hydroxides and the 4 hydrogens, they combine to make 4 waters. And then the 4 waters here and the 6 waters here, I said 4 and 6. 4 and 2 make 6 waters over here. So we've got 6 waters on the right, 4 waters on the left because the hydrogens and hydroxides combine. So we reduce both sides by 4 waters. The 6 goes down to a 2. That's how we get this overall chemical equation when we add those two half reactions together. And then the cell potential would be these two added together as 2.06 volts. So you see that with a positive cell potential, this reaction is spontaneous. So for hydrogen and oxygen to make water is a spontaneous process. Therefore, if we electrolyze water, it's going to go in the non-spontaneous direction. It's going to force the water to break apart. That's what I have brought this to demonstrate to you today. Try to bring this up close. So my power supply is plugged in right now. Remember, for electrolysis, we're forcing a reaction to happen, so we need some external power source. I have my positive post. It's got a red line connected to it with a piece of graphite on the end of it. Then I have my negative post. It's got a piece of graphite attached to it. And my water is not very clean anymore because I think the graphite is breaking up a little bit as I do this. Graphite seems to be affected by acid, and in my, when it's going back the other way, the one that's producing oxygen is actually making hydrogen ions and becoming acidic, and I think it's corroding the graphite. So I don't know if you can see this, but this is from last hour. I have gathered up some broken up graphite here in the bottom of the beaker. This will still work fine though. So I take my 2 electrodes from the power supply, put them into the water, not letting them touch. So they're in there. I want you to be able to see both electrodes. Let's see if I can get this to look better. Okay, so you can see both of these right now. Nothing is happening because I have not turned the power supply on. And also there is a dial on the power supply. Maybe I can move this over a little bit. And that has caused these to touch each other. Come on.
Try flipping the sides they're on.
What's that?
You try flipping the sides they're on.
Maybe if this says, well, they both are tending to go off that way. I want you to be able to see them both though. Okay. Yeah, I think maybe it's just the curvature of the beaker. Okay, so you can see them both. They can't be touching each other. If they're touching each other, it's going to short out my power supply. It's going to blow a fuse in it or burn it up, and we definitely don't want that. These things are really expensive, man. This is a budget buster. As dumb and simple as it is, it's just really expensive. Several $100s each for these little things.
For a battery? Not even.
It's like a battery. Yeah.
It plugs into the wall, it's not even a battery.
Okay, so the dial is turned down. You can adjust the voltage on these things. So I've got the voltage turned all the way down. So when I turn it on, you can see the light goes on. In the beaker though, nothing is happening. It's because the voltage isn't high enough yet. I don't know if the voltage is actually at 0. This says it's 1.5 volts. Well, this reaction is not going to happen unless I can overcome this natural 2.06 volts. So even if I turn it up to 2, this doesn't go up to 2. It goes from 1.5 to 3. So anyway, when I turn it up to the first one, if you're close to it, you can see. Did you see something happening?
Yeah, there's like bubbles coming out of the left.
Yeah, the one on your left, which is the negative post, has bubbles coming up out of it. The other one on the right also has bubbles coming up. Hey, Mr. Bubbles. But it's, ooh man, it smells too. It is not, maybe it was him and not this, I'm not sure. There are bubbles coming out of the one on the right. It's not as easy to see them. I'm going to kick it up one more notch, and that's going to increase the voltage, and you will see definitely an increase in the activity in here. The one on the right too, you should be able to see bubbles coming up out of that one. Okay, this is the electrolysis of water. At one of these terminals, if I get rid of all my writing on here, one of these half reactions in reverse is happening. At one of these, the reaction is the water is changing into hydrogen. At the other, the water is changing into oxygen. All right, now look at the overall balance equation. This really is all we need. The water at one of the terminals, or the electrodes, is changing to hydrogen, the other one is changing to oxygen. I'm going to turn it down for a moment, just so it stops working. I'll turn it back on in a second. But let's see if we can analyze this. If I take you back to this picture. Now I know before I showed you salt, molten salt being in the beaker that was being electrolyzed, but this time it's water. And the power supply is turned down. And there's a positive and a negative, so the electrons are getting pulled into the power supply. That means whatever's attached to the positive, which is the red one, is oxidizing. It's sending electrons out of itself and then into the power supply. So oxidation has to be happening on the right. The reduction then is the negative terminal, which is black, is sending electrons out of the power supply and they're going into the one on your left. Just the way this is being shown. No, it's not. It's opposite, because the red is on the left here, the red is on your right. Never mind. So anyway, the electrons are being pulled out of something where oxidation has to occur. So if it's water, the oxidation of water produces hydrogen gas. That was wrong. The oxidation of water is the oxygen, which is the -2. So this oxygen is, oops, and I'll even use the color coding on this. The oxidation, oh my gosh, I'm still using the wrong thing. The oxidation is where the water is changing into oxygen gas. The reduction is where the hydrogen is changing into hydrogen gas. I still color coded those wrong. The nuts. It's the oxidation is what's happening at the red. I can't live with that. So yeah, at the red post, something is giving off electrons, and it's coming down in oxidation number. So at the red, the hydrogen is reducing. So no, it's the oxygen. Sorry about this. I can get myself mixed up. I know that on the red, the electrons are leaving, so oxidation has to be occurring. I had it right before. Yeah, because the oxidation number is going up. From -2 up to 0, the oxidation number is going up. And then from +1 down to 0, the oxidation number is going down. Yes, that's correct. Because, and I try not to touch these, I shouldn't even mess with them. Did you notice one of these was bubbling more than the other one? The one on your left was bubbling more. I'll turn it up again. Now watch carefully. especially at the beginning. It's very obvious. This one that I'm pointing to is bubbling a lot more than the one that's next to it. So that should make sense, because at the reduction, according, with the black wire, the electrons are leaving the black wire, coming in, and the hydrogen ions, not really ions, the hydrogen positive one is reducing to H2. It's a 2-to-1 ratio. You see that coefficient ratio? There's twice as much hydrogen coming off the black wire that's being made compared to the amount of oxygen. So you see more bubbling where the hydrogen is being made in comparison. And by the way, I guess, at the end of class, if you'd like to, remember with the battery lab, we talked about hydrogen being made, and it does have a distinct smell. I'll run this thing and let you stick your face over it and smell the hydrogen, just so you know what I mean by it. It may make you cough, because, and this is not making a whole lot of hydrogen, but it's making enough to get your attention. I can smell it from here. Yeah, it's probably worth, while we're talking about smelling things and the physical properties of things, we should know what the smell of hydrogen is. Okay. It just got me. I'm going to step away from it for a moment until it dissipates. So this is the electrolysis of water. One terminal, the one attached to the red wire, is where electrons are being given off as the oxygen is changing to O2. And out of the other wire, hydrogen is reducing, because the other wire is the black one. The electrons are coming out of the power supply and forcing whatever is attached to this thing to reduce. That's the hydrogen. So water can both oxidize and reduce. We need to understand that water can both oxidize and reduce. The hydrogen will reduce in water, and the oxygen will oxidize. So we need to know that. There were questions earlier about aqueous sodium chloride. The first thing we looked at was liquid sodium chloride, and knowing what oxidizes and what reduces, well, there's only one option for each of those. That's very easy. However, when you have sodium chloride aqueous, that's different. It's different because not only do you have something that, like in this, the chloride ion can oxidize, but also the water that's there can oxidize. So the system has to make a choice. Okay, if two things in this mixture can oxidize, somebody has to oxidize. Which one is going to be the first one to oxidize? And when I say first one, the first one is going to oxidize until it's all gone, and then the other one can start to oxidize. So what we have to do is we have to look at what the oxidation potentials of all the things in the solution that can oxidize are. So chloride can oxidize to Cl2, and its oxidation potential is negative 1.36. The water that's also there, because this is aqueous, there's water in there, it can oxidize. The O is negative 2, you go to 0. The oxidation potential of water is negative 1.23. Neither one of those substances are very excited about oxidizing, but the one that's more positive, listen to this, when you have a choice between two different things that can oxidize, the one that's more positive in its oxidation potential is the one that's going to happen. So both of these are negative, but the water is more positive. So this half reaction is going to occur at the anode. Where oxidation has to occur, it's got to be the one that's more positive, which is the water. Yes?
Didn't you just look at the reduction potentials and choose the smaller one?
Yes. Yes, you could. Yeah. But what are you looking at the reduction potential of? Remember, on the table, these are flipped around. So you have to find them in the products of the reductions. Yeah, then take the smaller. Yep. Okay, so at the anode, the oxidation is going to be water changing into oxygen gas. So at the anode, if we electrolyze sodium chloride aqueous, where the anode is, which is the red one, we would see bubbling of oxygen coming out of it as oxygen gives off its electrons. At the cathode, where electrons are coming in, forcing something to reduce, there's two things in sodium chloride aqueous that can reduce. The sodium ion can reduce to neutral sodium. That's our first one. Sodium ion can reduce to sodium. It's got a reduction potential, it's a terrible reduction potential, negative 2.71. One of the worst things that reduce it. But then water also can reduce. There's water present. It is not excited about reducing, but it's much better at reducing than sodium is. So the one that's more positive in this case is also the water. So if you have aqueous sodium chloride, like if this is aqueous sodium chloride, it's kind of as if there's no sodium or chloride in there. Because at the anode, water is going to be oxidizing to oxygen. Oxygen bubbles are going to be coming up. And at the cathode, water is reducing to hydrogen. So the sodium and the chloride are doing nothing in this. And that's only because their potentials are so drastically more negative for each of those to happen. It is possible for you to electrolyze a solution with something dissolved and not have water being both oxidized and reduced. So very often with these kinds of situations where you're given, they'll tell you, okay, you have an electrolytic cell is prepared, and the solution that's being electrolyzed is aqueous potassium iodide or something like that. You have to look at, and so the question will be, what's being oxidized at the anode and what's being reduced at the cathode? And you have to look at, okay, what are all the things that can oxidize in this solution, and compare their oxidation potentials. The one that's most positive is going to be what happens. Then for the cathode, look at all the things that can reduce. The one with the most positive reduction potential is what's going to happen there. We'll do more examples of this tomorrow. I just wanted today to give you an introduction to what electrolytic cells are and the kind of things that we're going to have to do. So for electrolysis, primarily it's going to be what happens at the anode and what happens at the cathode. There is some math, some quantitative stuff that we have to do with this. We'll talk about that tomorrow too. But we'll do actual real examples of this tomorrow. Okay? So for the rest of our time today, we have several minutes left. I'm done with this. I will turn this back on. If you'd like to come and experience hydrogen, it will be here for you. Enjoy. Oops, that's really heavy.
All the way.
I don't know. I don't want to burn up my power supply. I treasure those things because they're so expensive. But Riley, you talked me into at least going one more notch.
Is this it's like get my face over it? I'm off.
Oh no, just go for the gusto. It got me again. I'm just trying to make sure they're not touching each other. All right, there you go. Let it generate a little bit, and then put your face right over there. See what you think. You smell something foul? I think that has a foul smell. It's almost like a rotten smell.
But is it hard to breathe if there's like a gas?
Come here.
That's very talented.
Can you pick anything up, John?
Not yet.
Is it hard to breathe if you're inhaling hydrogen gas?
Yes.
This is made for the electric flow.
That's just the way that this is noted.
It's not even hard to
The
breathe.
I can't
plus
smell it either.
is, that's the positive, port, and it's where electrons are getting pulled up. So this is positive, which pulls the electrons up. This is negative, which pushes the electrons up. It's just the symbolism that we use. Yes, yeah, really what's happening here is, inside the power source, electrons are being forced from that side to that side. So since this side is connected to whatever's down there, this is going to say, okay, well, I'm just going to grab whatever is going to be able to give me electrons and I'll pull them up from there. And those electrons get pushed over that side, which get forced down.
Which now I can
Yeah, yes, yeah. And the way that I always remember this is that think of the negative as the source of the electrons out of the power.
Oh, I smell it.
Out of the
Oh, I
negative.
smell it.
Ah, Sean, you got some. Good. Pull your hair back. Don't put your hair in there.
The water is turning
Source.
gray.
Oh yeah, there we go. We got some hydrogen being generated. Get over there and smell the hydrogen. You're advanced chemistry students. Come on, girls. Yes, in the power supply.
It's not hard to breathe. It just smells bad. You have to get pretty close. Be careful. Don't want the crap.
Oh, yeah, you guys are all getting caught up on this.